True. Always true. True. Always true.
Good afternoon, ladies and gentlemen. I hope you guys are doing well. I'm not gonna lie, I'm a little bit confused about fucking the end of our last lesson. So at the end of our last lesson, we were talking about, let me find it here, dynamic memory allocation. And during the lesson, we used the new word. I don't quite understand what exactly it does. I know that we are supposed to be using the heap somehow. I don't quite understand what exactly it means to do that. From what I can gather, it seems like because we are manually um, assigning data to an address, it seems like that address shouldn't change when we over the course of the program, however long that may run. But it seems I'm not quite sure what that does, and when I tried to do it on my own, I was embarrassing myself and not doing it correctly. Apparently, I'm not 100% on that stuff. No, that's me, not you. We're gonna go ahead and do this whole thing. But it's like, what do you mean on that, buddy? Okay. So we've got like, what was it? New integer. I assume I don't really I don't really understand it. I'm hoping to maybe get some more enlightenment here, but I'm not 100% sure if that'll be the case. Because at the end of the chapter we went on to dangling pointers. I don't know what a dangling pointer is going to be. That is kind of where I left off. I hope that you guys I hope you guys enjoy learning this shit with me. Time for smart people stuff. Not at all. I am a moron, okay? Ugh. Stop scratching the chair for no reason, dude. Or I can touch you on the head once and you can fucking sprint out of the room like I set you on fire. Holy shit. What was his deal? Okay, anyways. We're gonna go ahead and continue with this. Let's see. We know. Shut up. Shut up. Alright, let's see. Boom. Oh, look, it's oh, look. The code doesn't want to show up because it's the wrong project again. Yeah, so this shit, I didn't quite understand what this was all going to be used for. I had this at the end because, oh, code is running fine. Seemed a little bit of... Didn't really want to do. Anyway, let's get to this dangling pointers thing. Let me open a different folder. There we go. Close this. Alright, let's see how this goes. Dangling pointers.
In this lecture, we're going to focus on dangling pointers and show you how they can be bad. A dangling pointer is a pointer that is pointing to a valid address, and we have seen a few examples of this already. But in this lecture, we're going to focus on that and show you common solutions we can apply to these problems here. And dangling pointers are really bad. They are going to lead your programs to undefined behavior, and we have seen that that can crash your program many times.
Yep.
There are three kinds
that and
of
trying to
dangling pointers we're going to
delete
look at
data
in this
that
lecture.
has already been
First
deleted,
one
I
is
guess.
a pointer that is not initialized. The second one is a deleted pointer. And the third case may come if you have multiple pointers pointing to the same memory location.
Oh
and
no,
let's look at
that's
these
also a
cases
problem?
one by one. Here we have an example of a pointer that is not properly initialized. This is P number 5. It is a pointer to int, and it is not initialized. Doesn't really point anywhere, and it is going to contain junk address. If we try to dereference it, we're going to get bad things to happen because we don't really know which address is stored in there, and putting something in there might lead to a crash. So this is something you need to watch out for. The second kind of dangling pointer that can really lead you to bad places is a deleted pointer. Here is a pointer, P number 1. It is initialized with dynamic memory, and we can use it. For example, here we are dereferencing the pointer and printing the value inside and deleting the pointer. After we delete the pointer, don't really use it before you properly initialize it with some kind of memory. If we try to do that, this is going to be undefined behavior and your program might crash. So make sure
Okay,
you
so
don't
this
do
sounds
something
like
this.
kind
Another
of
case
review
is
of what
if
we
you
did
have
before,
multiple
kind of
pointers
stuff that we
pointing to the
understand,
same
stuff that we
address.
know.
And here is a simple example to drive the point home. We have pointer 3, which is pointing to dynamic memory here. We are using new
dynamic memory
in our braced initializer, and we are putting value 83 in that pointer location. And here we set up another pointer, P number 4, and we initialize that with another pointer. And if we print these things out, we're going to get that they contain the same address and they contain the same value. We're going to see that. If we delete P number 3 and try to use P number 4 later, we're going to get problems because this memory has been deleted by P number 3, but P number 4 is still pointing to that. And if it tries to use that, it's going to be
new is usually not used for ints, it's used for classes.
Behavior. So be sure you
Okay.
know these problems and try to avoid them in your programs. Okay, these are problems, but how do we solve them? Well, there are a few solutions. One is to always initialize your pointers. The moment you declare a pointer, make sure it is initialized. If you don't know what you can initialize that pointer with, put in null pointer first, and then you're going to put in an address later when you have a clear idea of which address you can store in. The second solution is to reset your pointers to null PTR after you delete the memory. That's the second thing you should do every time you call delete. That's going to give other developers or even yourself a chance to check and see if that memory location contains a valid address before you do that. And for multiple pointers pointing to the same address, you have to choose and make one pointer the master of the controller of the memory. And all pointers are basically going to be slaves, which can't release the memory, but they can read and do something with that memory, but they don't have the task of releasing that memory. And here is how you can apply solution 1, for example. We have pointer number 5, and we're going to brace initialize it. This is going to initialize it to
0, right?
null
Or
pointer.
null pointer,
The other thing
because
you can do is
it's a
initialize
pointer.
the pointer with dynamic memory, like we are doing here with p number 6. And this is going to put in the value, and we are going to be playing on the safe side. Now, if your pointers are initialized, developers have a chance to check your pointers against null PTR to see that they contain something valid before they use it. And if they see that it contains null PTR,
that's interesting.
They are not going to try and use it. And this is going to be very safe. For the second problem with deleted pointers, we are going to reset our pointers after we call delete. For example, here we have p number 7 initialized with dynamic memory, and an 82 is stored in. We can print it out or do things with it. When we delete the memory, we're going to reset it to null PTR so that other developers or even ourselves can check this memory against null PTR. And if it's different from null PTR, we can use it. If it's equal to null PTR, we're going to leave it alone and do something else. This is going to be very safe. If you have multiple pointers pointing
so much
to the same
text
address like we have here, then you're going to have to decide which pointer is the master pointer,
Only
and
use
other
slave
pointers
pointer?
are going to be slave pointers.
Oh,
and
no.
before use, all the other pointers
hmm.
are going to check against the master pointer and see that it contains valid memory, because the master pointer has the task of deleting this memory. Let's go through this and see how this could work in
Wait,
practice.
the master pointer deletes all of the memory?
P number 5 is our master pointer. We are setting p number 5 and initializing it with p number 8. We are putting things using p number 8. We can either use p number 8 or p number 9. This is going to work. But before we use the memory location, we're going to check against the master pointer. If the master pointer contains null PTR,
I didn't even notice that it was an
use
if.
this memory. If the master pointer doesn't contain null PTR, we're going to use this memory here. Okay, if you go down, you see that the master pointer is going to be releasing the memory. And if we try to use that memory after it was deleted, we're going to see that it contains null PTR, and we're not going to be using it. This is something cool, and it is really easy to implement these safety guidelines in your
It doesn't seem
programs.
difficult.
Now that you know about this, we're going to go to Visual Studio Code and show you this in action.
All right, let's see if we can.
Here we are
Let's.
in our
I'm excited to
working
try
directory.
this.
The current project is dangling pointers. So we're going to grab our template files pretty quick and put that in our project. And we're going to open this in Visual Studio Code. We are going to look at the first case of a dangling pointer, and this is a pointer that is not initialized properly, like p number here.
All right, let's get this written in here. So we're gonna have our int p number, and so this one is the dangling uninitialized. It doesn't seem difficult. Chat will remember that. Oh, please don't. Please forget that I said that. Uninitialized pointer. Hate p numbers. Why do you hate p numbers? What's wrong with p numbers, huh? Alright, see out. Oh my gosh. I can't buttons good. STD, see out. Case 1. Uninitialized pointer. See, or the thing that I hate is all of this, all these extra lines of text that we use. P number. Apparently I didn't put the P in. My P. Alright, let's go. And then we do P number. It looks like... So it looks like there's another one that he specifically has left out because it'll crash the program. I'm curious to see how... well, let me see. Maybe I can figure out why. He's more into PP number. Oh god. So many P's. So we have our uninitialized pointer. That's this one. It's not even like this. It's not even a not even null pointer. It's just uninitialized completely. So here P number this doesn't do anything from what I understand. It's like I think that this is the fact that this is here, so it's interesting. I didn't even notice that it was doing that the whole time. But yeah, so this one should be like, it should just be junk data if my understanding is correct. Right? Because this is completely nothing. And then if we try to dereference the nothing because it's uninitialized, it just crashes the program is kind of my understanding. That dangling again. Oh my god. That dangling.
If we try to dereference it, we're going to get something bad to happen. So let's see that, and let's go down and say that program is ending well. Just to know that we didn't get a crash, because a crash is basically going to terminate your program on the offending line. That's what it's going to do. So if the program works well and ends well, we're going to print this line here. Let's bring in GCC to build this program, and let's open a terminal so that we can run it. We're going to clear. The build was good, and we're going to run roster. You see that the program didn't end well. It crashed, and it crashed because we are trying to use uninitialized.
Okay, so when we did it here, when we did it without the line, it worked fine, as one would expect, right? And then we run it again, and this time we didn't get our little program succeeded, so it crashed on this line. Which is exactly what he's demonstrating, but just seeing it myself.
Memory. When the operating system is going to try and run this thing, it's going to see, this guy is trying to modify memory that doesn't really belong to him. It is a rogue program. I am going to kill it, and it is going to be terminated on this line here. This is really bad. You should avoid these kinds of situations. So don't do this. We are going to comment this out and show you another offending thing we can do in our program, and that is using a deleted pointer. If you do that, you're going to get something bad in your programs. So here we have a small example. We have a pointer to int. We initialize this with a dynamic piece of memory, and we're going to store in a 67, and we can print this out. This is going to work pretty well.
Alright, let's get this shit. So stdc out. I don't know why it's I don't know why he does an empty line here, but I'm gonna do what he does, because it's better all the better to understand my problems with. Deleted pointer, std in line, and then we have our integer pointer p number 1, and we have new int 67. Now, new is the thing that I kind of didn't understand in the last one. Like at the end of our last lecture, we did dynamic memory allocation, and I was kind of confused by what that was supposed to be doing. Like I guess I understand that it uses the heap. I don't quite understand what the heap is. And it seemed very I don't even I'm not even sure. It's just I was just confused by it, and it didn't seem to. I felt like I couldn't demonstrate that I understood it, and so I didn't. I couldn't.
But we delete the memory down here and we try to use it after we have deleted the memory. So the operating system is not going to be happy about this, because once the memory is deleted, it is no longer our memory, so we have no business dereferencing pointer 1 and trying to use that here. And we're going to get a crash, and this is something you should avoid. So let's try and build this and show you this in action. We are going to clear and run rooster, and you're going to see that program is ending well, but in some cases it might crash. And hopefully this shows you the danger that these things might put you into.
Oh, I didn't put the program is ending well thing. Whatever. It's not a huge deal because it still runs, which is partially concerning. Because this is nothing. This is junk data. This means because this thing was done. So that's a good way to fuck yourself over and make your life more difficult than necessary.
Sometimes your program is going to seem working fine, but sometimes when this memory that we are pointing to in P number 1 here is being used to do something really important by the operating system, you are going to get a crash. So you're not guaranteed to get the same behavior every time you run your program. Some of you might be saying, the program is working here, Daniel. Why are you making this such a big deal? Well, it is a big deal because you are not guaranteed to get the same results every time you run this program. So be
Yeah,
sure
we can see
you
that
really
actually
avoid
because
these kinds of situations. Let's try
this
and clear and run the program again. Hopefully we're going to see it crash, but we're not. Okay, so let's clear and rebuild again. And see that we have a better luck that time. Let's clear and run rooster. It is going to end well.
Yeah, I mean you can
You
see
notice
that the
that we are
numbers
trying to use a
change
piece of
every single
memory
time,
that has already been
which is
deleted,
not
and this
usually
is bad.
what you want
Don't
in
do
this
this.
with
Make
something like
sure
this.
you don't do something like this. We're going to comment this out again and show you another offending thing we can do with our programs. And bad things might happen if you try to have multiple pointers pointing to the same address, and that's what we have here. We have P number 3 and P number 4 here. P number 3 is allocating new space and it is pointing to it. We have an 83 inside, and P number 4 is initialized with P number 3. We can do that. So these two pointers are basically pointing to the same memory location. Let's run this and show you that.
Hold on, I want to see what the... Okay, so this is just an end line, and then we have our case 3, multiple pointers at the same address. And then we have our end line, and we have our... First we have our integer pointer number 3 using new int 83. Whoops. Okay, fine. And then we have our another pointer number 4. We do p number 3. Cout I keep doing this. P number 3, P number 3, and then we do the same exact thing, but for 4. Oh boy, oh boy. Let's see. And then we delete P3, delete P number 3, delete, like that. And then P number 4 points to deleted memory. Dereferencing it will lead to undefined behavior, crash, garbage, whatever. And then this one we have our cout. Like this. Delete PP, not financial advice. Holy shit, we haven't done not financial advice in fucking forever. For after deleting P number 3. All right.
With P number 3, we can do that. So these 2 pointers are basically pointing to the same memory location. Let's run this and show you that. We're going to comment out this delete statement here and run the program first to really prove that they are pointing to the same addresses and they contain the same values. Let's build and run. We're going to use GCC for that. And we're going to clear and run rooster, and you see that P number 3, the address is this, and it contains an 83. P number 4 contains the same things. So let's see what happens if we try to delete using P number 3 and using P number 4 later to try and read stuff. This is what we are doing here. And we're going to see if the program actually gets to end well. We're going to build again. The build is going to be good. Let's bring this up and clear and run rooster. And you're going to see that the program is also going to end well, but we are using a deleted piece of memory here, and anything can really happen. Okay, so you might get garbage, you might have
it's
really
definitely
any piece
garbage.
of junk inside, or you might get a crash in some extreme cases. So this is really bad. Don't do it. Don't try to use a piece of memory that you have already deleted through a pointer. And these are problems you might run into in your programs
that's a problem.
if you try to use dynamic memory allocation.
I was looking through old images I edited while finding my art references, and I have the PS1 Hagrid image that says "put dick in microwave." Not financial advice.
In a pointer if you don't know what that pointer is actually stored at. Okay, let's go down and look at solution 1. Solution 1 is to initialize your pointer to null pointer every time. If you don't have a value you can put in, use null PTR. That's what we are
seems
using
like
here
a good idea to me.
But we can explicitly put that in because it is good. And before you use a pointer, you have to check and see if it doesn't contain null pointer. This is how we do it. If pointer 6 is different from null pointer, we're going to use it. If it is equal to null pointer, we're not going to use it, and we're going to be playing on the safe side, and you're going to see that the program is going to end well here. If we have a null PTR inside, we can say else here and say invalid address, okay? And the user is going to know that they are trying to do something really bad. So let's try and check against P number 5. So let's go and store a null pointer in P number 6 to really try this out and show you that we're going to get this warning if we try to use it. And we're going to build with GCC and
P number 6
and run rooster. You're going to see that invalid address and the...
Okay, hold on. So this is the one that's checking our P number 6. check that P number 6 is not a null pointer. So in here, we go P number 6. Inspector gadget. STD and L. I do kind of wish that these would be colored somehow. I'm sure I can change that setting. I don't quite know how else. STD cout. Invalid address. Oops. Right. So basically, if P number 6 in this case is not null pointer, do this, else do this. So this should definitely be, this will be what it spits out, right? It should say that because that's what the video shows. So let's run it real quick. Clear. Yes, solution 1, invalid address.
The program is going to end well. And if we try to put this statement somewhere where we're not checking against null pointer, we are going to get a crash. So let's comment this out so that it's clear what it is we are running here. So if we run this, we're going to get a crash. We have seen that, but let's show this again and really highlight that we are solving the problem here. If we run rooster, the program is going to crash because we are trying to use an initialized memory. But if we try and check against null PTR, like we are doing here, let's do that. We're going to be playing on the safe side because it's going to tell us invalid address and we're not going to get a crash and the program is going to end well. This is really cool. So let's try and do that again.
Very, I mean, it stops you from fucking something over that you didn't plan to
and the program is
to
going
do.
to end well.
It'll stop it from crashing at least.
If we value inside, we're going to get that. So let's put that n and say new int and put in an 87, for example. It doesn't really matter what we put in. So we're going to build again. The build is going to be good and we can run rooster and you see that we are getting a value here if we are not storing null PTR in P number 6. And you can do the same checks against P number 5, but I think this is really enough.
I mean, that makes sense.
This is one way you can avoid dangling pointers. The next thing we're going to look at is if we are using a deleted pointer. And again, the solution is to set our pointer to null PTR after we delete it. Here we have P number 7. It has 82 inside. We are using it here.
All right, let's get our let's get his let's copy the lesson again. All right. So that's an empty line. This is just printing solution 2. STD and L. Then we have our integer pointer for number 7, which is going to be new int 82. It doesn't really matter the number, I guess. So then here it says use the pointer however you want. Oh, also I forgot. I should probably all of this stuff. This as well. Okay. Yeah, so we've got all of that. And then this one is cout P number 7. And then we have our P number 7. And since that is a pointer, this is the dereferenced of it. So this one is going to print the address, and then this one prints the information housed in the address. This is going to delete... I think this deletes the address and the info that's stored there. And then this assigns it, changes it so that the pointer is... It changes the pointer so that it's not there anymore. It's not pointing to that address. Oh, excuse me, I had to sneeze there. Oh. Check for null pointer before use. So then this is if p number 7 is not at null pointer, then we can do print this line of text, number 7, along with the info there. Okay.
Here and printing stuff out. We're going to delete it after we are done using it, and after that, the first thing we do is to reset it to null PTR. When we do that, other people or even ourselves have a chance to check it against null PTR, and we're going to know that it doesn't contain anything useful for our program. And if we do something like this, we're not going to run into all these weird problems, and our program is going to have consistent behavior across different runs, and this is really cool. So we're going to run this, we're going to get things printed out, and the program is going to end well, because right now we are checking against null PTR. We can even be explicit in showing the warning here. We can say invalid memory access, and if you run this program, you're going to really know this. So let's finish this up, and we're going to build, and the build is going to be good. If we run this and run rooster, we're going to know that we are doing an invalid memory access after we have deleted the pointer, and this is going to save you from possible crashes that you might experience if you don't do this. So this is a second solution you might want to implement in your programs, and we're going to comment it out and show you how you can get away from the problem of when you have multiple pointers pointing to the same address.
That seems helpful, because with this, the way that we have it written, if for some reason p number 7 gets changed between here and now, it'll show the other thing. I had a dream where alternates fought to the death in a dome arena, and I was the stadium lights guy, so I got to watch. Yeah, I had a dream last night that I fucking that I killed a man. Like, he came into my house after following me home from school, and I threw a yardstick at him, and then he walked in after I closed the door, and I shot him in the chest, and as he died, he said, "This was all just a misunderstanding." And I was upset, and I hit him in the head with my double-barrel shotgun. That was the dream that I had last night. Fucking weird. I was calling 911, and then I woke up. I was like, oh, well, that's good. Were you one of the alternates that then went to the arena? Maybe. Maybe. That would be fucking terrifying. I wouldn't want to fight my alter, dude. I wouldn't want to fight me. I feel like that'd be a bad time for both of us.
We are going to go down and put in the code. It is what you have seen in the slides, and it is really nothing new. So we have...
Okay, so here we have yet another empty line that we have for reasons that I'm not quite clear on. I think it's just to make it more readable. It's it seems very, I don't know. It seems like it's flourish more than function to me. Okay, Kyle Rittenhouse, that dream is dark as shit. Is there an alternate version of Adoring Fan? Oh god. P number 8. New int 382. P number 8 is the master pointer. I'll put in all this text at the top once I've got the actual code. Int P. Oh god, P. This one's number 9. It's going to point at P number 8. So let me get this tabbed over. Dereference the pointers and use them. std cout P number 8. P number 8. And then the pointer, or the dereference, I should say, which makes this, should store, it should print the number 382. And then it's if, oh god, okay, this is pretty long. Not P number 8 null pointer. If P number 8 is not a null pointer, I woke up with Inspector Gadget theme stuck in my head, but it said Inspector. Oh god, that's funny. I love that. Inspector. std cout P number 9, and then we have our actual P number 9, another bit shift, and then P number 9, and then I had let go of shift just a little bit too early. And then here we have delete P number 8. Master releases the memory. And this one says only use slave pointers when the master pointer is valid. He's in charge of penis inspection day. Oh, I have fond memories of penis inspection day during gym class. So, solution 3. For multiple pointers pointing to the same address, make sure there is one clear pointer, master pointer, that owns the memory, responsible for releasing when necessary. Other pointers should only be able to, oh my god, to dereference when the master pointer is I see a V here. I'm assuming it's valid. All right.
Pointer 8 and pointer 9 here, and pin number 8 here is pointing to dynamic memory, and the value inside is 382. Pin number
Okay.
9 is initialized with whatever we have in pin number 8, so they are going to be pointing to the same addresses here, but we have made pin number 8 the master pointer. So it is the only pointer that is going to be able to delete this memory location, even if we have multiple pointers pointing to that. Okay, so every time we want to use this memory, we have the option to check against the master pointer and see that we have some valid data inside. If it is null pointer, we're not going to use that, and we're going to be playing on the safe side. And this is really what we are doing here.
Okay. There's more text here that says std cout p_9 or number 9, I should say. My gosh. I mean, I knew there was going to be a lot of typing, but I thought he would be typing alongside me. I mean, at this point, I'm not surprised. It's more efficient for the lecture to not have to type every single line of code. And we go to our else std c error. Ooh, we haven't used error in a while. Warning. Trying to use an invalid pointer. And we want to go to here. We haven't used C error in forever. So like that, looks like. All right, let's see.
If we run this, we're going to see that the program is going to end well. The build is going to be good, and if we run rooster, we're going to see that we get things printed out. We're going to go through P number 8, we're going to print stuff. We're going to go through P number 9, we're going to print stuff. And if we try to use the pointer after the memory has been deleted, we're going to get a clear warning that we are trying to do something really bad. And this is really what you should aim for in your C++ programs that use dynamic memory allocation.
Okay, so let's walk through this, right? So obviously we have our empty line and our solution 3. Those are not a big deal. Then we declare our pointer, and we declare our master pointer, and then we have one of our slave pointers. So here, the next line of text that we're printing is this one, P number 8. So this one is its location in memory, and this is the information stored there. And then we go to the next one. And then here, if P number 8 is a null pointer, so this one, it's currently not. If P number 8 is a null pointer, we print this out. It looks like we don't have an else case, so it seems like if it just doesn't do, I think it just doesn't do anything if it's not. But it is, so it prints out this one. So we have P number 9, P number 9's location in memory, or what it points to in memory, which, because it's point number 8, is exactly the same as our last one. And then when we dereference that, it's exactly the same thing again, because again, they're both pointing at the same thing. And then we delete the memory from our master pointer. And we have it we change the address to a null pointer. So then here we check if the null pointer, or if number 8, the thing that was before, is equal to is a null pointer again. This time what we do is if it does, if it is fucking, I need to check. I need to run through this in memory. So this is not. So here we need, so p equals null pointer up here. This was false, so then false, false, if this is true. Okay, so then here, this time it is a null pointer, so then this is a, so then this renders this whole thing false. And then, so this first one doesn't run, and instead we get our second one, which says, which is the warning that we're getting here. So that's, I think I'm understanding how the pointers work. I'm still, I understand how new is functioning and what it does. I'm curious why we would need to do that. If it's being used for classes later, then I guess, or was it classes? Let me see. What did he say? Yeah, it's used for classes. If it's used for classes, then I think that maybe it'll make more sense then, because it should be larger. I think larger amounts, but we'll see.
And pointers. This is really all we set out to do in this lecture. I hope you know how you can avoid these problems with dangling pointers. We are going to stop here in this lecture. In the next lecture, we're going to see what can happen if this new operator fails to give you the memory that you want to allocate on the heap. And that's possible. Go ahead and finish up here and meet me there. In this lecture, we're going to...
Is this the next chapter of it? When new fails. Yeah, I guess it is. P equals equals P equals. P equals equals P equals. Yes, indeed. Yeah, so now we're on when new fails. It's so you don't need to store it in a variable before assigning it to a pointer. Oh, is that all it is? So like because we create a thing in memory, or so because we haven't declared an integer or whatever, or we haven't declared a variable, this allows us to directly assign pointers, or I guess directly do pointers. Well, no, it's also on the heap. Huh? This is like the only part of this whole thing that I'm like kind of iffy on and not really understanding, I don't think. Is new and how the heap works in reference to the rest of our code. Like I see this and I understand how it works. This is like we've created a pointer that we've called number 8 and it goes to this address. I guess. Or no, it has this information in it, but its address is changed. You said that not assigning the variable is the only thing it does, but it doesn't only do that, it does it on the heap. As opposed to the stack, right? Like all of this stuff, with the exception of this new thing, is on the stack, right? I'm not assigning the variable is the only thing it does. No. I guess what I was trying to say is that it's like we don't have to like declare a variable first. Like I don't go like I don't have to do like int 30 or some shit, or whatever, int an integer called a in 30 and then create a pointer to this variable. Instead, I just declare instead I'm able to just make a pointer that that goes to an address that has this information. Like I can just do int pointer and then have or no, int, where is it? It would be like new int and then have fucking some information in here. And I guess I just call this one like I can call this B, and this is our pointer. Whereas if I want to reference this thing, or like if I want to reference the address of A now, I have to make a separate thing for it, I guess. This is just kind of this part's confusing me. Like I couldn't just do yeah, this doesn't work. Apparently. A value type of int pointer. Oh, no, fuck. Cannot be used to initialize an entity of type int. Yeah. This stuff I don't quite understand. It seems like if I'm not using a pointer, I can't use new. And so I'm a little bit I think that's kind of what it's for. I'm like initializing when I use an int pointer, or I guess any pointer. I use I can if I'm initializing a pointer like this without without referencing something that I previously did. Let's see. So like if I wanted to do that, that's one thing. But then I can do int pointer C and then put the address of A in it. Right? Yeah. So like that's like these two lines, it seems to me, do the same thing as this one line, except that I had to create a whole separate variable, and it's still on the heap, or and these are still on the stack, whereas this is on the heap. Not that I really understand what that does for me. Yeah, this is the part that's confusing me. Using pointers seems pretty simple so far. It's just this thing that I just don't quite understand how it all works. Anyways, let's I'm gonna go ahead and save this, and then we're gonna make a new, what is it? Make a new folder, do it like that. Project 21. Do it like that, and then file, close folder, file, open folder. It's also, let's pin that to quick access. There we go. Okay. Boom. Okay. Let's do it. When new fails.
explore what happens when new fails. In the last lecture, we saw that we could use the new operator to allocate for new memory on the heap and use that to do stuff. And in most cases, the new operator is going to succeed. But in some rare cases, it is going to fail. And when you don't do anything about that failure, your program is just going to crash, and you might want to do something about that. I have to say that it is very rare for new to fail in practice. So you're going to see a lot of code out there that just uses the new operator. It doesn't really care about checking if the operation actually failed or succeeded. So this is a very rare case, but if you need to handle it, we're going to see how you can do that in this lecture. Here is a simple example that is try and force the new operator to fail. In the first statement here, we are using the new operator, but we are using a syntax that is going to try and allocate a lot of integers in one go. You see that it is an array, but we haven't really seen how we can use an array like this. So just think of this code as a piece of code that is going to allocate a lot of integers in one go. And we're going to try and make this fail. I have to say that this may give you an error on some compilers saying that you are exceeding the array size. If that's the case, no problem. We're going to find another way to get this new operator to fail. We are going to put a thing like this in a loop, and we're going to loop a lot of times, enough to exhaust the heap that is allocated to our program here. And when that happens, you're going to see that
is this dangerous to do? There's no way, right?
So new can fail. And if
like
you
right,
need
like
to
as in like,
play
is it dangerous to do like on my computer?
Handle that problem. And we have two ways we can handle this problem. We can go through the exception mechanism. This is a built-in way we have in C++ to check for errors and handle them. We can also use the std no throw setting in our new operator and force it not to throw an exception. And it's going to give us null pointer if the allocation fails. I know this might sound cryptic right now, but we're going to see an example shortly and you're going to understand this. Let's look at how we can use the exception mechanism. The exception mechanism is there in C++ to let you handle problems when they arise. And the way you use that, you wrap code that is potentially going to give you problems in try and catch blocks. You see here inside the loop, we are saying try, and inside the try blocks, we have the code that could fail. We have our new operator, and in the catch block, you see we have a catch block here. We're going to say that we have a problem, and we have a way of catching the problem. And if you look at this thing we have in this parenthesis, after catch, we have an EX variable, and we can ask it what kind of problem happened leading to this exception happening in our code. You can think of this like this. I realize we haven't really talked about exceptions. We are going to talk about them later in the course when we have enough tools to really understand what is happening. But now, think of them as a tool to handle when the new operator fails, and you're not going to crash your program. Your program will keep running. It will go through the end, but the new operation that you wanted to do here will fail, and you will be able to catch that. And this is a good thing. If you don't want to use exceptions, you can use the std no throw option. And this is a new version of the new operator you can use to tell the C++ system to not throw an exception when the operation fails. It is just going to return null pointer, and you can check for that and know that memory allocation actually failed. This is what we're going to talk about in this lecture. I hope you have an idea about this. We're going to head over to Visual Studio Code and actually try this in action. Okay, here we are in our working directory.
I think I understand what we're trying to do.
When new fails.
Just trying to force new to fail so that we can see what it looks like, right?
Always do. And we're going to put them in place. So when
and I guess this is our introduction to exceptions.
So we're going to do that and open this in Visual Studio Code pretty quick. And we are going to try and allocate a large piece of memory in one go. So the way you do that, we can do say int pointer. Let's call this data. It really doesn't matter. And we're going to say new int, and we're going to say that we want a huge amount of ints. Let's try and do that. And we're going to go down and say program ending well to make sure we know when we are ending this program properly. So let's try and compile this. We're going to bring up a terminal, and we are going to build with GCC as we always do, and the build is going to be good. Let's try and increase this number and push it to a really big number, and you see that we have made Visual Studio Code mad here. Array is too large, so they can't really allow us to do a really large array in here. Okay, so let's bring this down a little bit. And if we're trying to compile, the build is going to be good. And if we run Rooster, you see that the program is going to not end well. Okay?
Yeah.
So this is really a case where new fails. We can't really allocate this much on the heap storage that is allocated to this program here.
Terminate called after throwing an instance of std bad allocation. What std bad alloc? I don't quite std bad alloc is that's a new thing, but the std makes me think I should know what it is.
Remember when we revisited the memory map idea, we saw that each program is going to have its own memory map. The memory map is going to have a lot of sections inside. We have the stack, we have the heap. Our heap is not infinite, so we can run out. And we just ran out with this allocation that we did here. And our program is going to terminate. Immediately you see that it is not ending well. If
Seems
this
like
is not
it, yep.
working for whatever compiler you are using, we can go and do this through a loop. So what we can do, we can comment this out, and we can really loop many, many times, enough to exhaust the memory that is allocated for this process here, rooster.exe, in the memory map, in the heap section. That's what I mean. And if we do this, at some point, the program is going to fail. And we're going to get the same problem here. So let's build again. We're going to build with GCC. And we are going to clear and run Rooster. And we're going to see it's going to loop, and it's going to fail. We're going to see the failure in a minute, and we need to find a way to solve this problem. We have seen that we have two options. Let's comment this out and look at those solutions here. The first option is to go through the exception mechanism. We can also use the std no throw option. We're going to try the exception mechanism first, and what we do is wrap possibly offending code in try and catch blocks.
Oh, this is actually taking a minute to run. I might have needed to. Okay, there we go. Oh, I was getting worried there for a second. I was like, oh no, that took way longer than I anticipated. That was a little bit worrying. Okay, so this is the. Yeah, so this one crashed hard. I don't. Which is obviously like the point of what we're doing here, but it doesn't make me any happier to see it. Not really. Do like so. That is so convenient. Okay, so what we're gonna do, Gakwaya Sensei?
And we're going to say try here and put a block, and we're going to say catch, and we're going to say std exception, and we're going to put an ampersand symbol here. Just use this like this, and we're going to get a chance to really explain these things when we have enough tools to understand this. For now, think of this as, if I have code that is potentially going to fail, like the new operator here, I am going to put that in the try block, and if something goes wrong, we're going to get the error in the catch block. This is the way we do these things here. So for example, I can take my loop here and copy it and put that down below here. Okay, and I know that this line of code could fail. Okay, so I am going to wrap that inside try and catch blocks. So I am going to grab that and put that in my loop. Let's do that and align this a little bit. And we are going to take the potentially offensive code and put that in the try block. And when the operator here fails, something goes wrong, and we're going to catch the problem in the catch block. This is what we mean here. Again, we don't have enough tools to understand why we are doing this thing here. What is the meaning of this ampersand symbol? We're going to learn about that later in the course, but for now, we want to put together something good enough
C++
for this
is usually 1
program not to
microsecond per
crash
line
like
of
it
code,
was
so you can
doing
calculate how long
right here. Okay,
it
we're
will,
going to catch the error and say
a 4
something
will
went
go on.
wrong. And we're going to print out
It's a
what
long
actually
time.
went wrong. We're going to say ex, and we can call a function called what on this. And we can say std endl. Let's hide this pane here because we want to see clearly what is happening here. This is how you can prevent your program from crashing, and it is going to end well because now we have handled the problem and we haven't caused a crash like we were doing down here. Now we're going to try and build this code. Let's bring it up a little bit so that it is not messy here.
Ooh, okay, so I forgot the so for size t 0 I is less than I is less than 1 0 0 0 0 0 0 0, and then we increment by 1. And then this one goes ends here. I think that's the way that this is written. So we have our try line that ends here, and we have this which ends here, and then this next one. Okay. Terminal run task.
And we're going to build with GCC. The build is going to be good, and we're going to clear and run rooster, and it is going to do its thing. It's going to keep looping around.
Round
and
and round
it's
and
going to say
round it
something
goes.
went bad. It's going to hit a point where all these allocations are going to fail. And if we really wait for it, it is going to end. And we're going to see that it's going to end well. Let's try and hit Control C and terminate it because we don't want to wait for this amount of time. And let's bring that down to 100 and increase this number here. Let's see if that actually works. So we're going to build. So
Oh,
now we
holy
just want
shit.
to see that the program is not really
It fucking, like, all of a sudden my terminal got full of fucking text, and my my YouTube decided to shit the bed a little bit. I don't know if those events are related. Holy shit. It's still going. That's a long time that it goes on for. Just fucking. Wow, it's still going. Holy shit. Something went wrong. STD bad allocation. Something went wrong. STD bad allocation. Fucking insane. Insane in the. Uh-oh. Well, that's me. I think I broke my shit. This is not good. I can't tell. What? What? What the fuck was that, dude? What the fuck was that? I'm not gonna lie. I'm not gonna lie at all. That pisses me off just a little bit. Like, don't get me wrong. I understand this kind of thing can theoretically happen on accident, but holy shit, don't do it to me on purpose, you fucking dickheads. My whole shit done broke. My whole fucking shit. I don't even know, is it on the same fucking thing on YouTube? Probably not, right? It is. Oh my god. I'm shocked by that. Holy shit. Here, let's go ahead and do wow. But then also fucking this one. What the fuck? Okay. What the fuck? Wow. Oh my god. Okay. Are we good? Am I square? Am I back now? I don't even know. Doesn't feel like I'm back. Very, 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 very anger. Very don't like. Very upsetty. Very, very upsetty spaghetti. Very, very not happy about that. Okay, so we're just gonna go ahead and I think from this point on, we're just not going to do stuff that he tells us explicitly is going to fail or cause problems. Because the last thing that I need is to brick my shit accidentally. So we're going to avoid that at all costs. Jesus fuck. Yeah, it definitely doesn't feel like I'm back. My whole shit done broke. Yeah, it says I'm unstable on Twitch. And YouTube. Well, YouTube says stream is healthy. Poor network connection detected. The fuck do you mean? Alright, how far along was this? I don't even know is the problem. Let's see. So this was when new fails. So it should be before the 12 hour, or before 12 something. I would like to find... Okay.
Color fails and you fail to set up the color, you may show your user interface in black and white and keep you're going to handle that problem. And we have two ways.
You know, and this was supposed to be the catch. That's what this was supposed to be. That's what's kind of annoying.
This is a built-in way we have in C++ to check for errors and handle them. We can also use the std no throw.
This is very, very annoying.
In our new operator and force it not to throw an exception, and it's going to give us null pointer if the allocation fails. I know this might sound
I actually had to
right
restart
now,
my
but
whole
we're going to
fucking
see an
computer in
example
order to get my shit
shortly,
back.
And you're going to understand this. Let's look at how we can use the exception mechanism. The exception mechanism is there in C++.
Yeah, we're not fucking with any of this.
And the way you use that, you wrap code that is potentially going to give you problems in try and catch blocks. You see here inside the loop.
Yeah, and it failed to fucking catch it last time I tried. What the fuck?
We have the code that could fail. We have our new operator. And in the catch block, you see we have a catch block here. We're going to say that we have a problem and we have a way of catching the problem. And if you look at this thing, we have parentheses after catch. We have an EX variable. And we can ask it what kind of problem happened.
I didn't even get to see.
This exception.
I have no idea what went wrong.
You can think of
I mean, I know what went wrong, but it didn't get the chance to tell me. It just died.
We are going to
My
talk
screen
about
went
them
black.
later in the course when
All
we
of my
have enough
windows that I
tools
could
to really
see
understand what is
were like,
happening.
they looked
But
like it was
now,
Windows
think
fucking
of
Vista.
them as a tool to handle when the new operator fails, and you're not going to crash your program. Your program will keep running. It will go through the end, but the new operation that you wanted to do here will fail, and you will be able to catch that. And this is a good thing.
The fuck I
If
will.
you don't want to use exceptions, you can use the std no throw option. And this is a new version of the new operator you can use to tell the C++ system to not throw an exception when the operation fails. It is just going to return null pointer, and you can check for that and know that memory allocation actually failed.
Alright, we're just gonna
This is
not
what we're
make
going to talk about in
mistakes
this lecture.
of this
I hope
magnitude.
you have an idea about this. We're going to head over to Visual Studio Code and actually try this in action. Okay, here we are in
we tried it,
our
and
working directory. The current project
it
is
was
when the
bad.
new fails.
Extremely,
We are going to grab our
extremely
template
bad.
files,
We're
like we
not
always
doing it.
do, and we're going to put them
Not
in
again.
place. So when new fails, that's the lecture. So we're going
Let's
to do
keep
that
going.
and open this in Visual Studio Code. Pretty close. And we're going to
Alright, we gotta fast forward back through all of the shit that we already
I know
seen.
that this line of code could fail. Okay.
Yeah, that line of
So I
code
am going to
fucking
wrap that
killed my whole
inside try
computer.
and catch blocks. So let's do essentially in the this pane here because of the problem, and we haven't caused a crash like we were doing down here. Now we're going to try and build this code. Let's bring it up a little bit so that it is not messy here. And we're going to build with GCC. The build is going to be good, and we're going to clear and run rooster, and it is going to do its thing. It's going to keep looping around, and it's going to say something went bad. It's going to hit a point where all these allocations are going to fail.
Yeah.
And if we really
It started doing this to me, and then my whole shit broke.
And we're going to see that it's going to end well. Let's try and hit Control C and terminate it because we don't want to wait for this amount of time.
Yeah,
And
no,
let's
I
bring
didn't do that.
Down to 100 and increase this number here. Let's see if that actually works. So we're going to build. For now, we just want to see that the program is not really crashing. So we're going to run rooster, and you see that it's going to keep running, and at some point it's going to fail to allocate memory, and it's going to say something went wrong. But if you keep going down, you're going to see that the program is ending well. So what is happening here is that the new operator actually failed, but we caught the problem and could handle it in here. So what is called handling the problem? You're going to handle it in whatever makes sense in your program. If we were, for example, trying to set up a color in some widget in your application, and the color fails, and you fail to set up the color, you may show your user interface in black and white and keep running your program instead
Use
of
less
getting
for?
across.
What do you mean?
This is just a way to show you that you can handle stuff when new fails.
Probably
This is
used up
one
your
way we
RAM.
can solve
Oh,
the
almost
problem. So
certainly.
we're going to look at the second way. The exception mechanism is the first. So we're going to comment this out because we're going to see another way. And let's do that. We can also use the std no throw setting on our new operator when we are allocating for new memory. So we're going to do that. And we're going to bring up our loop here. We're going to reuse that for this. Here we're not going to be using the exception mechanism, so we're going to do something like this, get rid of the try and catch block, but we're going to still be in our loop here. So what we can do is pass the new operator a parameter and say std no throw. And when we do this, if new fails, we are going to get null pointer stored in data here. So we can check this against null pointer. We can say f data is different from null pointer, and we can do whatever we want to do. We can do that and say stdcout data allocated, and we can try and compile this program. So what we're going to do is run this through our compiler, through GCC, and you're going to see that the build is going to be good. And you see that Visual Studio Code was giving us a squiggly line because it can't really understand this, but this is going to go through the compiler and it is going to work exactly how we expect. So let's try and run this program. We're going to ignore Visual Studio Code for now because the build was good. We could build with GCC and we saw that this was building successfully. So we can
Yeah,
clear.
if it's finished successfully.
Let's clear properly and run rooster, and it's going to say data allocated a few other times, and the program is going to end. You see that? The
So do you
program is not
understand it yet? Are
crashing
you a
because we
master?
are also handling the
Redbird, my
problem,
shit done
but we
just
are going
exploded.
through a new mechanism to do that, and that's using the std no throw option with our new operator here. This is really all we set out to do in this lecture. I hope it is very clear that the new operator can fail, and you have a couple of options
That didn't answer
at
the
your
question.
hands to handle
I think it
things when
does.
you
I think it
fail.
does answer the
You can
question.
either go through the exception mechanism
No,
by
I
using
am not a
try and catch
master.
blocks like we did here,
The shit
or you
exploded
can use
and
the
is
std no throw
it does not
option.
work.
We are going to stop here.
Or it
in
worked,
this
but like
lecture.
my
The next one we're going to learn
like
about
I needed to
null
restart my
pointer
whole computer in
safety.
order to fucking get my
Go
shit
ahead and
back.
finish up here and meet me there. In this lecture,
Null pointer safety. I'm a little bit of I'm not gonna lie, I am a little bit salty about like running a program that the tutorial is telling me to do and then fucking my whole shit having to get restarted. I am a little bit salty about that. I'm not very fucking happy about it. You know, like I understand, you know, doing stuff for the purpose of a tutorial, but this is fucking very it feels very, very bad to me. I don't like it. Like, it's one thing if I did it and it's like, oh, I fucked up, I made a mistake. Many things explode for pyrotechnic people, but for pyrotechnic masters, many things don't. Is that supposed to make me feel better? The pyrotechnic master isn't supposed to tell a random pyrotechnic wannabe how to blow themselves up. That's not usually how that goes. All right, let's see.
we're going to explore the concept called null pointer safety. And this is a series of measures you take to make sure that when you are using a pointer, it contains a valid address. If you don't have a valid address inside, you don't use that pointer. And we do that through a series of checks we can do against null pointer. For example, here we have a pointer that is initialized.
He should have preambled it with "Don't do this. This is just a demonstration." Oh, he definitely didn't. The whole point.
And
the whole point was to use this try and catch thing. That was the whole point. And it just fucking, instead of doing that, it crashed my shit. So I don't trust this operation. I just don't think it works the way that it's intended to. Or it works in a way that I don't understand, and when I wrote it in, it fucking broke. Lazy said I could maybe use less up here, you know, and maybe that'd be fine. I'm not gonna fuck with it. I'm not gonna test it. I don't trust it at all. this can go fuck itself. We're doing whatever the fuck this is.
what we can do is check if P number doesn't contain null pointer, and this is how we say it in C++. And if it contains null pointer, we're not going to use it. We're going to say it points to an invalid address. This is something you can do. It is simple in nature, but it is going to save you lots of trouble. This is one version we can do this in, but we can also
never saw STD no throw in my life
and use it like this. If it contains null pointer, we're going to get the message printed out that we have an invalid address. If we have something other than null pointer, we're going to have a valid address, and we can do something with that. This is going to work because a pointer can also be implicitly converted into a Boolean expression that our if statement expects here. And it is going to work exactly how we want here. So we're going to see this in a minute when we hit Visual Studio Code. Before we do that though, I want you to be aware that you can call delete on a pointer containing null pointer without doing the check here. It is going to be okay.
Optimal programming doesn't need to catch exceptions. It has its uses in whips.
You have
Works
to
in
check
progress.
for null pointer before you do anything on your pointer. And they even do that before they call delete. I have to break it to you that it is safe to call delete on a pointer that contains null pointer. So you don't need to do something like we have here. Say and check if p number 1 and then delete p number 1 and reset that to null pointer. This is really overkill. You can
That's a
call
lie.
delete on
Don't listen to
pointer
him.
and it is going to be fine even if it contains null pointer. Now we're going to go to Visual Studio Code and see these things in action. Here we are in our working directory. The current project is null pointer safety. We're going to grab our template project and we're going to put that in the current project that we are interested in. And we are going to open this in Visual Studio Code open folder. And we are going to put in a verbose null pointer check. What we are doing here is nothing new. We have a pointer called pNumber. It is a pointer to int, and it is initialized to null pointer through implicit initialization here using braced initialization. And we are checking to see if it contains null pointer. If it does, we're going to say it contains an invalid address. If it doesn't, we're going to say that it has a valid address. And you see that we are using a negation here. You can
The best programs behave exactly as you expect them to. So basically, it only does something that you don't expect it to if you have skill issues. Which, I mean, that makes sense. Verbose null pointer check. I did the wrong thing. Verbose null pointer check. As to null pointer, and then if pNumber null pointer, we can do pNumber points to a valid address, and then pNumber, and then this is the, then we do else, pNumber points to an invalid address. No, we don't need to draw on anything. Hey, how you doing, 2040 Denise? Optimal programming is linear, so you're never supposed to use loops either. Yeah, well, obviously you expect them to throw an exception so you can use them. What? I am not understanding most of what's going on. Alright, so here, I mean, it's just checking that this is that this isn't a null pointer. If it points to a valid address, then it just gives us the address. If it doesn't point to a valid address, which it shouldn't because this is null pointer, unless null pointer is considered a valid address. I don't think it is, though, because it's like it's literally a non-address. But then, like, I guess 0 is a non-number. It's weird. Let's run it. Yep, invalid. Okay.
You can do this however you want. If we try to build this with GCC, let's see what we get. The build is going to go through, and if we run Rooster, we're going to see that pNumber points to an invalid address because it contains null pointer. But
yes,
if we try and set up a new variable, for example, and say pNumber, and let's use dynamic memory, we have learned about that, and initialize that with a 7, for example, and when it points to a valid address, we're going to print whatever is in there. We know how to do that. So we can say pNumber, and we're going to print whatever is inside, and say pNumber through dereferencing, and we're going to say stdndl. Now the pointer is not going to contain null pointer because it contains the address of the memory that was allocated on the heap here. But once we do that, we have to remember to release this memory. So please remember to release your memory after you are done using it. So we're going to say delete p number after that, and we need to reset it to null pointer. In this case, it really is useless because nobody is going to be using this pointer anymore. The program is about to end, but it is a good practice to do this even in this case, because once this way of doing things is burnt into your memory, it has become your habit. You're going to be writing
Just wait until he gets into corporate
code.
programming with
Now we're going to
singletons,
try and run
factories,
this.
and
So we're going
monads to
build
impress the
again. The build
managers.
is going to go through,
Oh no.
and it is going to say that we have a valid address in memory, which is this guy, and what is inside is a 7. And now we are writing Cypher C++ code through null pointer safety here. We can also do a direct check using p number without checking if it is equal to null pointer, because this is verbose, but it is something you will see in practice. You can also do something like this and say if p number, and you're going to get exactly the same thing. So if we have some valid address inside, we're going to print that. Let's print the same thing as in the previous code here. And if we build and run, we're going to get exactly the same thing.
Wait, if p number? I don't understand. Wait. Hold on. Let me figure out what the fuck is going on. So we have exactly the same thing a second time, functionally. But then we do, instead of checking if it's a null pointer, we just have if p number. P number points to a valid address. He won't be doing design in this course. I mean, it goes all the way up to whatever the fuck polymorphism is. That is the extent of my of this tutorial, I should say. So we're gonna go ahead and it goes to here. Am I
Previous code here.
Oh, okay. So you just had that other thing out. So we're gonna go ahead and do. We're gonna go ahead and just copy this, put it up here.
And if we build and run, we're going to get exactly the same thing. Okay, so let's clear because the build is good. Let's clear and run rooster. You see that we get exactly the same thing. And if we didn't initialize this guy with a new dynamic piece of memory, we're going to get that the memory is invalid. The address we have in the pointer is going to be invalid. And we're going to print that out through our code here. We run rooster, invalid address. Okay, the last thing I want you to see is that it is okay to call delete on a null pointer. And we're going to say that here. So we're going to go down here and put in a piece of code. We are setting up a new pointer, p number 1, initialized with null pointer. If we call delete on it, this is going to work really well, and you're not going to get a crash or anything.
How goes stuff? It goes. It goes. It could be better. It could be worse. I'm a little bit annoyed with the way that they handled this shit, which actually crashed my whole shit and necessitated a reset in order to unfuck it. Or I don't know if it necessitated it, but it takes way. It seemed like it was gonna take way longer if I just waited for whatever the fucking problem was to go away. So here we delete p number. Do like this. The battle continues. It does indeed. It's okay to call delete on a null pointer. Calling. Wait, why the fuck would you say the same thing twice? So int p number 1. And then we can delete p number 1
valid C++ code. So if we try and compile this, it is going to work fine. And you don't really have to do a null pointer check before you delete like this, because that's overkill. You see that the program built successfully, and we can clear and run it.
Watch
and
out,
we're
the
going to get
llama is
exactly the
spitting.
same things we had before. So some people are going to do something like,
What the hell?
they're going to check for null pointer, and they're going to say if p number 1, for example, is not equal to null pointer, and they're going to say something like delete here, and they're going to do something like this. And this is going to work, but it is really overkill. You don't need to do this test because it is safe to call delete on a pointer even if it contains null pointer in the first place. So you don't need to do things like this. This is going to work just fine. Don't be afraid to call delete on a pointer because it might contain null pointer. This is really all we mean by null pointer safety, and I hope I gave you a few examples to make this pretty clear. We are going to stop here in this lecture. The next one, we're going to learn about memory leaks. Go ahead and finish up here and meet me there. In this lecture, we're going to learn about memory leaks. And a memory leak is when you have lost access to a piece of memory that was dynamically allocated to your program. You basically lose the pointer that was pointing to that dynamically allocated piece of memory.
The only time I've ever heard of memory leaks is when people talk about like Google Chrome and shit, and certain games that start running very slowly after a certain amount of
The value
time.
inside is going to be a 67. This P number is our only key to manipulate that memory. And it is the key through which we even go to release that memory and return that to the operating system. But notice what we do down here. We are setting up a new number variable. It is an integer and it is allocated on the stack because this is a local variable. It's not a pointer. It's not dynamically allocated. And we take the address of number and assign that to our pointer. The moment we do that, we have no way to release the memory that was allocated to P number in the first place. And if we do that, the operating system is going to think that this memory is ours, but we don't have a way to release this memory anymore because the pointer that was helping us access this memory has been repurposed to point to this number variable here. I hope you see that. And a memory leak is something like this. When you lose the pointer, that would otherwise be used to release the memory. And your program is basically going to keep using this memory, and the operating system is not going to have a way to reclaim this memory. So it is useless. So you are no longer using this memory because you can't access it and do things with it. And the operating system can't use it either because it thinks it's your memory. Hopefully you can see that this is a really bad situation. And you should avoid these things in your application.
So, okay. So basically, this pointer is pointing at this thing, and then we have another integer that we've created. Kitty, get your asshole off my arm. We have another integer that we've created here, and then when we reassign P number, then this is just kind of lost. Huh. I don't know why. Yeah, it's not good. I don't get.
Avoid memory leaks like a plague. This is one situation in which we can have a
But it
memory
is
leak.
legal code,
Here
and
is
it
another
works.
example
Other
where
than
we
that,
have double allocation. We have a pointer P number 1. It is pointing to dynamically allocated memory again, and the value inside is a 55. If we use this pointer to allocate new memory, the first memory that we were pointing to is going to be leaked. Again, it is the same thing. We have lost access to the first memory. Now we are pointing to the second dynamic memory that was allocated to contain the 44 here. And again, this is a memory leak. Your program has lost access to the memory containing 55 here, and the operating system also thinks that you are using this memory because you didn't explicitly return it to the operating system through the delete operator. Again, memory leaks are bad. Do avoid them in your programs. Here is another simple example of a case where you might have a memory leak. You go in a nested scope like this and allocate a new piece of memory dynamically, of course, and point to that through P number 2 here. But P number 2 itself is a pointer, and it is a local variable nested in this scope. When this scope ends, P number 2 is going to die, but the dynamic memory itself is not going to die. You just lost access to it, and you can't access it. Again, this is a memory leak, and you should avoid this in your programs. Memory leaks are really bad.
You have to use... So in a case like this, in order to avoid it being a memory leak, you would need to then, I guess, delete and like make this point at nothing again. In that you would need to delete this, essentially this this memory, so that it's not so that when the program dies, it doesn't end up as a leak. Right? Is that kind of how it would go?
Cases, they might even lead to your program crashing if your program keeps running for an extended period of time. Think of programs like those running in servers, for example. They can even run for 3 months without stopping. And if your program is increasingly leaking memory, the operating system is going to think that you are taking too much heap memory. It's going to terminate your program, like we saw in the lecture.
Well, we know how bad that can be.
Where the new operator failed. So if you allocate too much memory, then your program can really take the next operations you're going to do with new are going to fail, and your program is going to terminate. The message here is memory leaks are bad. You should avoid them in your programs. And whenever you think that you're no longer using a piece of memory, make sure you delete it and return it to the operating system. You're going to be writing much safer C++ code. We're going to head over to Visual Studio Code and actually try this. Here we are in our working directory. The current project is memory leaks. We're going to bring in our template files, and we're going to put them in place in the lecture on memory leaks. And we are going to open this in Visual Studio Code. We are going to clean this up a little bit. Bring this up. Here we have a variable called pNumber. It is a pointer to int, and we initialize that with the address of a piece of memory that is allocated dynamically on the heap. We store a 67 inside, and here down you see we set up another variable on the stack. Again, this is a stack variable. It lives on the stack. It's not on the heap. And we take the address of this thing and assign that to our pointer here. The moment we do that, we have no more way we can access this dynamic memory, and we have leaked it. And this is really bad. The thing is, this program is going to compile. I don't think compilers have a way to stop you from making mistakes like this. So you really have to be careful and make sure that you are not leaking memory in your program. So if we run this program, it's going to run. It's going to run and finish. Let's say that it is ending well. Okay, so we're going to build and see this run. The build is good, so we can clear and run rooster, and we're going to see that the program is ending well, but we are leaking memory here because the dynamically piece of memory that we allocated here wasn't released to the system, and when we did this assignment here, we just lost access to it. So the operating system is going to think this memory belongs to this program that is ours here, but your program is either not going to be using this piece of memory because we have just lost the key that would allow us to go and do something useful with this memory here. So this is something bad, and you should avoid it. The second example of memory leaks is when you do double allocation on a pointer. For example, here we have pNumber1 again.
Now changes pNumber to point to address 2. pNumber1 pNumber has been lost and now Memory has leaked. Alright. So this is double allocation. So here we have a pointer to p number 1, new int 55.
And we are going to make this point to an address of a piece of memory that was allocated dynamically on the heap. The value inside is going to be 55. But we are using this pointer again to make it point to a new piece of memory containing the address of a newly allocated piece of memory on the stack, on the heap, I mean. And this is really bad because, again, once we do this, we lose access to this memory here and it is leaked. The program here is not going to have access to it, and the operating system is going to think we own this memory and it is going to be bad. And down here, maybe you can go and say delete number 1, p number 1, but this is not going to release the memory here. It is going to release the memory here with the 44, and the memory containing 55 here is going to be leaked. Let's be good C++ citizens and reset our pointers after we delete. So we're going to say p number 1 equals no pointer, and we are going to be playing it safe here. And again, we just leaked the memory here, and it is something you should avoid in your programs. If you run this program, it is going to run just fine. So let's see that, because I don't want to leave you with programs containing errors. If I run roster again, it's going to end well, but it is going to be leaking memory here. So we don't want to leak memory. Avoid this like a plague. We're going to comment this out and show you that you can also leak memory when you have some nested scopes in your programs. Okay, let's go down here and
It seems like that would be the easiest way to leak memory, is with nested scopes.
Nested inside the main function, and inside the scope here we are setting up a new pointer, and it is going to be pointing to dynamically allocated memory, and that memory is going to contain a 57. The only key we have to this dynamic memory is this p number 2 pointer here, but this p number 2 pointer lives on the stack itself. So when the scope here is going to end, p number 2 is no longer going to be accessible, and the memory is going to be leaked. If you really want to play it safe, you can go do whatever you want with the dynamic memory, and when you are done with that, you can delete that piece of memory here while you still have access to p number 2. But if you don't delete here, in the scope where this thing was declared, if you hit the end of this scope, you're going to lose access to this pointer, and you will be losing access to this dynamic piece of memory, and you're going to be leaking memory because you're not deleting it. Even if you want to delete it, you won't be able to do that because you don't have a key that is going to lead you to that dynamic memory. So if we try and do delete p number 2 here, this is not going to compile because we don't have access to p number 2. P number 2 is scoped inside this nested scope here. This is what I mean. So be sure you are aware of this memory leak problem. The cases we have seen here are really extensive enough to give you an intuition on how this is bad, and you're going to be avoiding this in your programs, and you're going to be on your way to become a better C++ developer. This is really all we set out to do in this lecture, to learn about memory leaks, show you a few examples of them. I hope now you understand them. We are going to stop here in this lecture. In the next one, we're going to learn about dynamically allocated arrays. Go ahead and
Dynamically allocated
and meet me there.
arrays.
In this lecture, we're going to look at dynamic arrays.
That is... Okay, so this is the last section before we finish the chapter. So let's do this. Let's get it... I kind of want to say let's get it over with. I'm not gonna lie, having my whole shit crash like midway through the fucking through the lesson has really made me very salty, and I'm not super happy about about that happening. So, I'm gonna be poopy about it all day.
And these are arrays you can allocate on the heap, and they're not going to be stored on the stack like we have seen before. The arrays we have learned about so far have been living on the stack. We want to see how we can allocate arrays on the heap if we happen to need that in our applications. Arrays are allocated on the heap with the new operator. We can also use the std no throw version of the new operator if we don't want exceptions in our C++ programs. Here is a simple example of how you can do that. We have a pointer called psalaries. It's going to be a pointer to double, and it is going to contain the address to the dynamic memory that we allocate on the heap, which is going to contain an array of doubles of this size here. Okay, this is an array that is going to be initialized with junk values because we are not initializing that explicitly. So this is something you need to be aware of. Okay, pstudents is also going to be containing the address of an array that is going to be allocated on the heap. We are using the std no throw version of the new operator because in this case, for example, we might not want exceptions, and we're going to say that it is an array of events. It's going to be this size, but we are using braced initializer, so this is going to be initialized to 0. All the values inside are going to be initialized to 0. This is what we mean here. We also have a p-scores array. We are using the std no throw version of new, and it is going to be this size and initialized with 1, 2, 3, 4, 5. Okay, if
so why am
the array
I
is bigger than 5, the remaining slots are going to be
why am I arraying?
Just like we saw
Oh Jesus Christ!
we
Why am I using dynamic
previously
allocation for an
that will
array
store on the
specifically?
stack. This is really how you work with these things, and I hope it is super clear. Again, we are calling the new operator. This is going to allocate however memory space is needed to store these things on the heap. So if this array is going to contain 10 elements, we're going to allocate enough space to contain 10 double elements on the heap, and we're going to be pointing to that with the psalaries pointer. That's what we mean here. Once you have your dynamic array allocated on the heap, you can try to do things with it. For example, we can try and loop through the scores and print them out. Here you see that we are using the angle bracket syntax and the pointer arithmetic syntax. It is going to work equally well. You can choose whatever you want, but I just wanted you to see that you can use both versions here. The next logical thing to think about when you talk about dynamic memory allocation is how you release the memory to the operating system when you're no longer using it. And this is the syntax to do it with arrays. You say delete.
It's the same thing, isn't it?
Brackets, and you say the
Oh,
pointer
well, it has
that was
the
used
angle
to
brackets, making
allocate
it
that memory in the first place. And after you do that, you have to
delete
remember
matrix,
to reset the pointer to null pointer
and then
because you are a
to
good
null.
C++
Okay.
citizen. And this is really
I am a
all
good
we
C++
have to say
citizen.
in this lecture. This is how
I'm
you
a citizen
dynamically
plus.
allocate arrays on the heap. Before we head over to Visual Studio Code and play with this though, I want you to keep in your mind that arrays you allocate dynamically on the heap are very different from the arrays that we have learned about before. And that's because they don't work with std size and they don't work for range-based for loops. And the reason for all these limitations is that when you do something like this, the array really decays into a pointer and it loses information that would otherwise be used to deduce the size that is used by std size.
But then,
and there are
so
other
why would I
things that are
use it?
used by the range-based for loop that they lose when you store and refer to them using a pointer like this. That's why we have this limitation. Keep this in mind if you are using a dynamically allocated array on the heap. You're going to be using other techniques to deduce its size, and it is not going to work with a range-based for loop. So we will have to use other kinds of loops that we have learned about in this course, and it is going to work pretty well. This is really all I had to share in this lecture. Now I think it's time we went to Visual Studio Code and actually tried this out. Here we are in our...
I'm kind of confused as to why I need to do arrays dynamically allocated arrays in the first place.
And we're going to put
I
that
don't.
in the current project and open
It
this
seems
in
more
Visual
limited and
Studio
more
Code like
complicated.
we always do. And we are going to go down and put in some starter code we can play with here. We're going to click on this file icon to remove this pane. And we're going to try and show the code here. And again, you see that Visual Studio Code is freaking out when it sees the std no throw version of the new operator here, but it is going to work when we hit the compiler. Okay, so we are allocating 3 arrays on the heap dynamically, and we are going to be storing the addresses to these arrays and these pointers. For example, p salaries is going to store the address to this dynamic array, which is going to be living on the heap, and it is going to be the same case for p students here and p scores. I don't think there is much to explain here because we have already learned about arrays. We know about the size of an array. We know that it is a piece of contiguous memory location that is going to be storing variables of the same type. This is really what we're going to have. So let's try and compile this and see that it actually goes through our GCC compiler, and it is going to work fine. And another thing you should notice is that this is really compiling even if what we are using to store the size of the array is not const. Remember, for stack arrays or static arrays that we had on the stack, we had to make sure this guy here is const. Okay? That was a requirement, and if you didn't fulfill that, your code wouldn't compile. Now you see that with dynamic arrays, the code is actually compiling even if it's not const. And this is something you should be aware of. Let's build this again. I just messed up my thing.
Hold on, I gotta catch up. Mr. Gakwaya, you're going a little quick for me. I don't have the luxury of copying a shitload of code into my thing the same way you do. 1, 2, 3, 5. Like this. Okay, so let's take a look at what he has written. So this one is changing to a const size t. Different ways you can declare an array. Dynamically. And how they are initialized. So this one is salaries array will contain garbage values. Okay, that's understandable. This one is all values initialized to 0. That one's convenient and useful. Allocating memory space. For an array of size double vars. First 5 will be initialized with 1, 2, 3, 4, 5, and the rest will be zeros. That much is understandable.
Things here. And the build is good.
Because our
If we go
size is
down
10.
and run it, we're not going to see anything really because we're not having any output in this program. But this is how you can allocate space for a dynamic array on the heap. Now let's try and print some of the data in these scores here. Let's go down here and actually do that. We are going to do a null pointer check because we want to make sure that memory was actually allocated for the p scores array. And after we do that, we're going to look for size times, and we're going to be printing whatever element is at each iteration, the index at each iteration. And you see that we can either use the angle brackets notation or the pointer arithmetic notation. It is going to work equally well.
Okay, so let's get that in there. So, null pointer check and use the allocated array. So, if, that's another thing I should probably do. let's indent all of that. If P scores, then we go std cout size of scores. It's a regular pointer. And then this one says size of P scores. And then we end our line. And then it's successfully allocated memory for scores. That's fantastic. Print out elements. Can use regular array access notation or pointer arithmetic. So this is our for size T I is less than size increment I. Cout value P scores. We do I. And we have a pointer to P scores plus I. STD and L. I still don't understand if P scores. What does this mean? Oh, this isn't a pointer. This is dereferencing P scores. Because P scores is an array pointer. By the looks of it, right? No. P scores is P scores is a pointer. And it points to an array. So dereferencing the pointer should give us the index, the location of, or the information at each at wherever I is in the array. It's kind of my understanding.
If we build this, let's bring up our terminal. We haven't opened one. And let's go down and clear and run Rooster. You're going to see that successfully allocated memory for scores. And we're going to be printing the data. First, using the angle brackets notation. Second, using pointer arithmetic. And you see that it is working pretty well. One thing you should have noticed now is that we haven't actually released the memory that we have allocated here, and this is something really bad.
Yeah.
So we're going to see
so
how we can
all
do
of
that.
this is leaked.
We have allocated space for salaries, P students, and scores. So let's go down and do that, and we're going to say delete. And we're going to have angle brackets because this is an array we are releasing memory for, or to be exact, a dynamic array which was allocated on the heap. So we're going to say P salaries, and we're going to reset that pointer to null pointer because we are good C++ citizens. So we're going to do that, null pointer, and we're going to do the same thing, delete. We are deleting space for a dynamic array, so the angle brackets here, the square brackets, I should say, and we are going to delete P students, I think, yes. So we're going to say P students, and we're going to say P students, and we're going to reset this to null pointer. And we're going to do the same for p-scores. Let's grab this here. That's what we want. No, that's not what we want. We're going to say delete and say square brackets ourselves, and we're going to say p-scores, and we're going to release that and say p-scores and reset this to null pointer. Now
All
we
of these are now
playing
null
it
pointer.
safe, and our program is going to release the memory that we allocated in these
Oh,
three statements.
hello. I don't
If we build the
understand
program, it is
Russian
going to go through well.
or
So we're going to
Ukrainian
build
or
with
whatever
GCC,
language it is that you're. I don't speak any Cyrillic
and
languages.
we are going to clear and run Rooster, and it is going to run pretty well. You see that for p-scores, we initialized the first 5 elements, and the remaining elements were initialized implicitly by the compiler to 0, and you can see that here. I don't think I explained this, but this is my chance to explain this. I hope you understand. The next thing I wanted to explore before we close this video is the difference between static arrays and dynamic arrays. A static array
Yes, please
is an
explain
array
the
you
difference.
allocate on the stack like we have been doing before, and you do it using a syntax like, let's say, scores, why not? And it is going to be an array. Let's say it is going to contain 10 elements. And we are going to put in our values in the format that we know, and we're going to go all the way to 10. Let's put in a 10 here, and we're going to end this with a semicolon. This array is cool, and you can loop through it, you can do all kinds of crazy things with it, but I am going to emphasize 2 differences we have with dynamic arrays. One is that this guy is going to work with std size, so we're going to say cout. Okay, this is going to work. If we compile this, we're going to get a good build, at least I hope. Yes, the build is good. And if we run Rooster, we're going to get scores size is 10. The other thing is that you can use a range-based for loop to loop through this guy here. So for example, we can say for auto score, S for score in scores, and it is going to work. So let's go down and say what we are doing here, or we can even say a single line to separate things here. I don't want to be confused, so I am going to do something like this so that I know where my output here is going to start. So I am going to build this with GCC, of course. The build is going to go through, and if I clear and run Rooster, I am going to see that the size is 10, and I am going to print my elements here with a range-based for loop. Okay, let's see how these things behave when we use a dynamic array. We are going to set up a similar array, but on the heap, which is going to live on the heap. This array here is the static array in that it is going to live on the stack. You have to be aware of these differences. Okay, we're going to do another one which is going to live on the heap. And the way we do that, we say end pointer. Let's say p-scores 1 to make sure this is different from p-scores that we have on top here. And we're going to have 10 elements inside. And we can even initialize this guy exactly like we are doing here. But the data is not going to live on the stack. The data is going to live on the heap. If we do something like this, first, let's make sure that the code compiles. We're going to try and run this through GCC. And watch the compiler output here. The build is good, so this is valid C++ code. We can try and use std size on that, and we're going to go down and do that. And if we do that, we're going to say p-scores size, 1 size, and say p-scores. If we try to pass this pointer here, you're going to see that Visual Studio Code is going to freak out because this won't work. The array here has decayed into a pointer when we refer to it using a row pointer like this. So we can't really use it inside std size. So if we look at this, we're going to get a weird compiler error, but this is going to be the problem here. Okay, so you can't do this with dynamic arrays. This is one limitation. The other is that you can't use dynamic arrays like we are using a range-based for loop here. So if we grab this loop and try to work with it on p-scores, for example, this is something somebody might want to do. Let's say p-scores 1, okay, and try to print something inside. You're going to see that this is not going to work. The compiler, Visual Studio Code, is not going to like it first. And if we try and run this through GCC, we're also going to get a weird compiler error. And the problem is going to be that P-scores is really not an array. It is just a pointer that is pointing to some location in memory. That's all it is. And it doesn't have information that could be used otherwise to loop through elements
Interesting.
like we can do for a real static array that is living on the stack. Again, let's be super clear here.
Could I not... If I do this, is that not dereferencing it? I guess it doesn't. I feel like that should be the case, though. Like, this doesn't work because p-scores is a pointer, but if I dereference the pointer, surely it can give me the information that's inside there, right?
And say that this array is going to live on the heap. You have to understand these things. But this is really not a big limitation because you can store the size of this guy in some variable and refer to it if you need that. And you can loop through the array exactly like we did here using size, and it is going to work pretty well. So don't be afraid to store your arrays on the heap if that's what you need in your application. It is going to work pretty well. You just have to be aware of some limitations that come with doing things this way here. This is really all we set out to do in this lecture. I hope you have a better idea about dynamic arrays. You set them up like this. The size here doesn't have to be const like we have with static arrays, and they have a few differences compared to static arrays that were stored on the stack, and that std size doesn't work for them, and they don't work with range-based for loops. Other than that, dynamic arrays are really cool, and you should use them when that helps whatever it is you are designing. Welcome to this new chapter.
Whoa. Okay. So that is the end of pointers. I'm still not 100% sure about new. I'm not 100% comfortable with using it. I don't know exactly. Like I kind of get it, but also not really. It's like I have this like high-minded idea of like what the heap and the stack are, but that is not what I have for like I don't quite understand it like in a real sense. I do know that if I overload it, it will crash my whole shit, and that I'm not going to be happy about that. It's quite the it is quite a I don't even know what to call it. I think I do think that it's I'm a little bit salty still about having my shit crash like an hour ago. That was really I didn't think that was very good. I didn't like I know fundamentally everything's fine, you know, no as far as I can tell no permanent damage to anything, but it still made me very unhappy to have have a a a teacher tell me, "Hey, do this thing," and then when I did that thing, it crashed my shit. This. I don't like this. This is very, very annoying. The fact that this didn't even execute all the way through, and my shit was busted until I had to reset my computer. I had to hold down the power button and make that shit fucking turn off. That is that upsets me. I don't like having to do that because I've had to do that before, and it has resulted in damage because I've had to do it many times, or so at the time at least. So I believed I had to do. But anyway, so that's the end of pointers. So we're gonna go into references tomorrow. I don't know exactly how long this one seems like it'll be pretty short. But I think I'm going to just go ahead and let tomorrow be a pretty short one. Because we're just gonna do the chapter. It looks like it's only half an hour long, so for us that's gonna be like maybe an hour. When you have any variable that is more than 8 bits, you should use new and save it to a pointer, because you save memory when you copy it. Because you copy the address instead of all of it. I mean, I guess I'll take your word on it. I don't... it makes, like, I guess that makes sense to do, because if you use new, then it just kind of creates a new, or like you save that memory specifically for that thing, and supposedly it can't get fucked with by anything else, and it's not supposed to be fucked with by anything else. And then having the pointer point to it, I guess, is probably better. But I don't know. I guess like I said, I'm still not like super comfortable with it. We'll see how I feel in like a week or two after maybe I have to use it a little more often. But anyways, guys, I'm going to hop off here. I'm gonna get some food. I hope you guys have a good one. We're gonna continue playing Warcraft later tonight, so that'll be fun. And then after that, we can we'll be back tomorrow with references. This should be a short one. We're gonna let tomorrow be a pretty short lesson, I think. Hope you guys have a good one. I'll talk to you again in the future. Bye, guys.